Hi everyone, here's your chapter 17 homework, first part. Okay, so since you guys want to have some help from me, so I'll go ahead and do this homework along with you. Okay, the first one is asking which of the following compounds does not have an alpha hydrogen. So what are alpha hydrogens? Alpha hydrogen means when you have a carbonyl group, right? Alpha hydrogen, you have a carbonyl group, and then you have some carbons attached to it, and this carbon is called alpha carbon. This is also alpha carbon. Hydrogens on that carbon are called alpha carbons. So this one has how many alpha carbons? Two alpha carbons. And then the hydrogens, how many alpha hydrogens? We have 5 alpha hydrogens. Okay, now if you have this molecule right here, that's a terrible group. I don't like that. I'm going to erase it. Okay, let me redraw that. If you have this, these are all methyl groups. And how many alpha carbons do we have? We still have 2 alpha carbons. How many alpha hydrogens do we have? All of these bonds that I have drawn, they are methyl groups. So this is the first alpha carbon, second alpha carbon. Do we have any alpha hydrogens on carbon number 1? No, all of them are methyl groups. And how about carbon number 2? Do we have any alpha hydrogens? Yes, because it has only 3 bonds. The one that is not drawn is hydrogen. So this one has only 1 alpha hydrogen. Let's say you have a compound like this, carbonyl group, and then you have alpha carbons. This one has 3 methyl groups. This one also has 3 methyl groups. Do we have the alpha carbons? Yes, we do. Do we have any alpha hydrogens? No. So there are no alpha hydrogens. Okay, so those are the alpha hydrogen. Now let's find out in compound number 1, which one is our alpha carbon? This is the carbonyl group. Next to carbonyl carbon is the alpha. That's the alpha carbon right there on the benzene ring. Do we have any hydrogens in that alpha carbon? There are no hydrogens, right? Because if you draw the benzene ring, it's like this. COH. Now the carbon, alpha carbon, which is this carbon over here, right? So how many bonds are there already? 1, 2, 3, 4. There are 4 bonds already on that carbon. So there are no alpha hydrogens. So for the first compound, there are no alpha hydrogens. And how about the second compound? Do we have any alpha hydrogens in the second compound? Which is this one over here. Okay. Do we have any alpha carbons? We don't even have any alpha carbons because we have only 2 hydrogens. Okay, so there are no alpha hydrogens here. How about number 3? This is the carbonyl group. This is the alpha carbon right there. So we have 2 alpha carbons. So this is an alpha carbon and this is an alpha carbon. But do we have any hydrogens there? No, all of them are some carbon groups, so there are no alpha hydrogens. How about number 4? This is your carbonyl carbon and this is going to be your alpha carbon. On that alpha carbon, we have 3 methyl groups. Do we have any alpha hydrogens? No. So which of the following does not have an alpha hydrogen? Meaning all of the above does not have an alpha hydrogen. Okay. Okay. Next one. Which of the labeled hydrogens in the following compound is the most acidic? Most acidic one. So we have hydrogen number 1, 2, 3, 4, 5. Now in this one, this carboxylic acid hydrogen, that is the most acidic one, this hydrogen right there. Carboxylic acid, acidity is pKa, acetic acid about 4.5. So it can range from around 3, 4, 5 area, carboxylic acids. Okay, so that's that. But this hydrogen is acidic, but it's not as acidic as carboxylic acid hydrogen. Okay, so pKa of that number 4 hydrogen ketone, I believe, is about 15 maybe. You can look it up, I forgot. Okay, but it's less acidic compared to hydrogen 5. So the correct answer is carboxylic hydrogen, which is the 5th hydrogen. And then the next one, which of the following underlined alpha hydrogens is the most acidic? Now the acidity depend on how many carbonyl groups are next to that alpha hydrogen. Okay, so now in the first one, you have a CH2 group, and then you have 2 carbonyl group. And for this one, the B, you have only 1 carbonyl group, and C also you have only 1 carbonyl group, and then D has a 1 carbonyl group and a hydrogen. E has 2 carbonyl groups, but one of these is a ester group. Okay, so one of these is a ester group, this one over here, and this is a carbonyl group. Now with the ester, when you have a ester by the alpha carbon, so remember we learned about that the oxygen of the ester also competes for the resonance. So because of that, A would be the most acidic. Okay, A would be most acidic because there are 2 carbonyl groups, so the negative charge that we generate, but once the hydrogen is lost. Remember we talk about the acidity depend on how stable is the anion CH3, CO, CH. Once that hydrogen is lost, this becomes CH. Now, if we can stabilize this by delocalizing electrons, that will make it very stable. So that is one resonance structure that we can draw. Also, we can draw another resonance structure like that. So the negative charge is delocalized. That will make it very stable. So now A and E. So remember A is this one, and E also has 2 carbonyl groups. But in E, you can see the ester oxygen also competes for the resonance. So as a result, A hydrogen would be most acidic. Okay. And number 4, which of the labeled hydrogens in the following is the most acidic? Again, which one do you think here? Is it 1, 2, 3, 4, 5? It's going to be carbon number 3. Hydrogens on the carbon number 3 would be the most acidic. Okay, that's the one closest to the carbonyl group. 5, which of the labeled hydrogens is the most acidic again? Now you know which one to choose. Which one going to be the most acidic? It's again going to be, hydrogens on carbon number 4, because there are 2 carbonyl groups next to that carbon number 4. Number 6, which of the following is a beta diester? Beta diester. So you need to choose if you have a diester, 2 esters. Now remember the functional group ester. So what is the ester functional group? Ester is this one. You have a carbonyl group, oxygen, and an alkyl group. Okay, now it's talking about a diester. So in that case, which of the following is a beta diester? Now A, do you see 2 esters? No, right? So it has only 1 ester. And then B, what about B? Do we see two esters? We do, right? So here you can see COOCH3, COOCH3. So if this is the carbonyl group of interest, and this is your alpha, and this is going to be your beta, so then that means it's a beta diester. Beta position, and the position that we talk about has two esters, so the correct answer is B, because there are two esters. It's a beta diester. And C is not diesters, D also not diester, E also not. So the correct answer for that is B. Number 7. What carbon nucleophile attacks bromine in the acid catalyzed alpha bromination of a ketone? What carbon nucleophile attacks bromine in the acid catalyzed alpha bromination of a ketone? Normally it is the enol ion that attacks bromine. Okay, the enolate ion. Let me see if I can show you. Which slide, so then you can refer to the lecture slides. Look at the lectures. It's the formation of the enol from the ketone, and then you can see how it is being attacked. I'm gonna tell you what is the slide number, so you can refer to that in your slides. Acid catalyzed halogenation. Yeah, so that is going to be slide number 15. Okay, slide number 15, refer to that. Slide number 15. Acid catalyzed alpha bromination of a ketone. So what first happened is, if this is your ketone, since it's acid catalyzed, so this will first protonate. Alkyl group. And then it's going to form the enolate. So if I expand it, carbon, hydrogen, hydrogen, and another hydrogen. So this is the alpha carbon, and even a water molecule can take this hydrogen and form this intermediate, which is HCH double bond OH R group, and then the halogenation, bromine. If it is bromine, so now you have the enol. Once the enol form, this is how it's going to attack now, and the pi bond. Okay, so that is the acid what carbon nucleophile. So it is the enol, so this is called enol. So it is the enol nucleophile that attacks bromine in the acid catalyzed alpha bromination of a ketone. So this is explained in slide number 15 in your lecture notes. Okay. Excuse me. And then the next one, what is the product of the following reaction? Now this reaction it's a bromination in the presence of an acidic medium. So in the presence of an acidic medium, okay, what's going to happen? How many bromine will get added to the alpha carbon? So for the acid catalyzed bromination, normally only one bromine will add on to the alpha carbon. Okay, if this is acid catalyzed bromination. I'll go ahead and erase this part. Okay. Now this question asks, in the presence of acid catalyzed reaction, it's only one bromine. So the same mechanism that I just showed you earlier, it will only add one bromine to the alpha carbon, CH3. So the bromine will add here. Okay, that's going to be the answer. It's this one over here, not ED. Okay, that's for the acid catalyzed. And then the next one, what is the product of the following reaction? Now we have a base promoted halogenation. So for the base promoted halogenation, what's going to be the answer is you can add, you can replace all the alpha hydrogens with bromine. Okay, and this is in your lecture slide. The mechanism is on 17, but the main reaction you can see on page slide 16. Okay, so this is slide 16. Base promoted halogenation. All the alpha hydrogen will be replaced. So in that case, you also have the mechanism on slide 17. COC, CH3, and then you will have this. Okay, that's going to be the answer for this one. Yes, so now you know what's the answer. And then the next one, the Hell-Volhard-Zelinsky reaction in wall. What is that reaction? So we talk about that the Hell-Volhard-Zelinsky reaction in slide 18. So slide 18. I'm giving you the slide so you can refer to the lecture notes to understand further. Okay, so these mainly involve halogenation of an acid, alpha bromination of carboxylic acid, alpha bromination of ketones, aldehydes to acids, bromination of alcohols. Okay, so if you refer to the slide 18, you will understand that this reaction talk about bromination, alpha hydrogen bromination of a carboxylic acid. So then the correct answer is alpha bromination of carboxylic acids. And then the next one, what is the product of the following reaction? Now it's again the same reaction, HBZ reaction. You have a carboxylic acid, you are adding bromine, phosphorus tribromide, and hydronium ion as a second step. So what is going to be the product? So you will again halogenate alpha hydrogen, alpha carbon replacing the alpha hydrogen. So it is also similar mechanism. Again, this is on slide, about the same slide, 17, 18, 19. Yeah. So you can refer to this one with the steps, slide 19. Slide 19. So this will halogenate alpha carbon of a carboxylic acid. Okay, that's going to be the product, and only one hydrogen will be replaced. And the previous one is that's a ketone. Okay, now this is a carboxylic acid. That's number 11. Number 12. Which of the following reagents converts a ketone completely to its enolate ion? Which one do you think? So now we are talking about enolates. Which of the following converts ketone completely to its enolate ion? Is it a hydroxide ion like sodium hydroxide, or it is a lithium diisopropyl amide, diethylamine, lithium hydroxide, sodium hydroxide, pyridine? Which one did we talk about that gives us almost 100%? We talk about this in slide 20. Okay, so this is in slide 20. We talk about this concept, and with the hydroxide it only gives about less than 0.1% because the pKa of the water is 15.7, whereas the pKa of the ketone is around 17. Whereas with the lithium diisopropyl amide, the resulting diisopropylamine group has a pKa 35, meaning which is a weaker acid compared to the pKa of the starting ketone. So this information is on slide 20. So we use the base lithium diisopropylamide as a strong base to completely convert a ketone to an enolate ion. Okay. Number 13. Which of the following most rapidly alkylates an enolate ion? Now, we also talk about once the enolate ion forms, now it is going to react with the alkyl halide in a SN2 fashion. Remember we talk about that, that is a SN2 reaction alkylating an enolate ion, and this is on slide 22. Okay, refer to slide 22 that I talk about this. That once the enolate ion is formed, it attacks the alkyl halide in a SN2 fashion. Which substrates works well for SN2? Is it the primary halides, secondary or tertiary? It's going to be primary halides. Now the bromobenzene. Benzene is a bulky group, 2-methylbromobenzene. Again, that also more substituents, tertiary butyl bromide, tertiary group, isopropyl, and then the methyl bromide. So which one is going to be the primary halide out of these? Is it the bromobenzene, 2-methylbromobenzene, tertiary butyl bromide, or the isopropyl bromide? So your bromobenzene is going to be this molecule. This is bromobenzene. And then we had 2-methylbromobenzene. Two-methylbromobenzene. Two-methylbromobenzene or tertiary butyl bromide. This is tertiary butyl bromide. And then isopropyl bromide. This is the isopropyl group. Or methyl bromide. I'm still wondering if I wrote the 2-methylbromobenzene correct. I believe so. Bromobenzene, 2-methylbromobenzene, looks like it's correct. Anyway, so methyl bromide is the primary halide, so that will work well with SN2 fashion with the enolate. Okay. Okay, so the next one. What is the product of the following reaction? Now we are using LDA to form the enolate in the presence of tetrahydrofuran, a THF, which is a solvent, and in the second step you are adding methyl iodide. Now LDA is a little bit bulky base. So if the base is bulky, it's a strong base. Where do you think that it's easy for it to get the hydrogen removed? So we have hydrogen here, there is alpha hydrogen here, and also there are hydrogens on this side. So this, if you say this is the side A and these are hydrogen B, which one is more accessible hydrogens, hydrogen A or hydrogen B? Hydrogen B is more hindered with a methyl group, so the hydrogen A would be easy to remove because it's more open. So you can form the enolate ion here. So this is CH3, you can form it here. And then when you add the methyl iodide, it attacks the methyl group and leave iodide group. So then your product going to be no benzene. So the product is going to be this, right? So that's going to be the correct structure. And then which of the following methods can be used to prepare the following compound? Okay, so you want to add a methyl group on the alpha carbon of this compound. Now the first one. So you have alpha beta unsaturated carbonyl compound and a methyl iodide. Do you think we can use this one, the method, first method? No, you cannot. Okay, but number 2, so you add LDA, lithium diisopropyl amide, and then you add THF, methyl iodide. Looks like that is something we can do. So because you can make the enolate here with LDA and then attack the carbon and then leave iodide, so that can add alkyl group there. That's number 2. And for the number 3, we have ketone and we have a secondary amine, and with that we can make an enamine. We learned how to form the enamine. So you put the nitrogen. Initially you will have that, but then it will form this, right? And then when you add the methyl iodide, it can form alkyl group here, methyl, and then in the next step when you add the hydronium ion, you basically remove the nitrogen part and then you can get back to your ketone. So that is also a possible way to do that. So 2 and 3 methods we can use to alkylate that ketone. And where do we find this information? Alkylating an enolate, esters and nitriles, synthesizing amine. Slide 27, 28. Slide 27, 28. You can refer to this. Okay. Next one. What is the product of the following reaction? And with LDA, lithium diisopropyl amide, always is alpha hydrogen that's going to be lost, and then it can be reacted with the alkyl halide. So let me show you. Okay, so that information you can refer to with the LDA. Page 22 again. Okay, similar information you can find in page 22, slide 22. Okay, again when you add LDA, so there are 2 alpha carbons, so any one could be lost alpha hydrogens, and then once you make that carbon ion enolate, gonna go here and then the leave chloride. So your product going to be CH3, CH2, CO, CH, CH3, and here you can have CH2, CH3. Okay, so you find out which one it is. It could be any side, even it could be this carbon ion I form or this one of these. It's going to be the same. So what is the product of the following reaction? Again now you will find this one alkylating an enolate ion, alkylating esters and nitriles. Acyl groups. Alkylating alpha carbon via an enamine, or you can also do it with LDA. So the same thing here. The only difference now here, instead of a alkyl halide, you have an acyl group. So first thing is, again you are going to make an enolate. It could be either that carbon or this carbon, one of those. Okay, once the enolate is formed, it's going to attack this carbonyl group, and then the pi bond will open up, and then it's going to reform the pi bond, and then the leave chlorine. So this is chloride. This is happening in few steps. I put everything on one place. Okay, so this product is going to be something like that: CH3, CH2, CO, CH, CH3, CH2, CH3, and here you can have a carbonyl group CH2, CH3. Okay, like that. So you will find which one is the correct one. CH3, CH2, CO, CH, CH3 looks like. Look like A is the correct answer, isn't it? CH3, CH2 carbonyl group, CH, CH3 carbonyl, yeah. Look like A is the correct answer. And then the next one. What is the molecular formula of the product of the following reaction sequence? So you have a ketone. You are going to react it with secondary amine. You will form enamine. Then you will react it with ethyl bromide. And then when you hydrolyze it, you will get the ketone back. Okay. So we have done these kind of reactions before. So we can go ahead and draw the formation of enamine. It's a single bond right there. So this is the enamine. Once enamine formed, so that's what happened in the first step. And then the second step, you're going to react it with this. CH2, and then you will lose your bromide group. So it's going to form this. And then the second step, when you add water and hydronium ion, you simply remove this part and then you're going to get your ketone back. And then when you count how many carbons are there in your product, 1 2 3 4 5 6 7, how many hydrogens are there? 2 4 6 7 8 9 10 11 12, and an oxygen. So you count the number of carbons and hydrogen and oxygen to find the molecular formula. Number 19, in a Michael reaction, addition to the alpha beta unsaturated carbonyl is initially a 1,2 addition, Diels-Alder 1,4,1,5,1,3. What is it? We talk about alpha beta unsaturated carbonyl compounds. That is basically a 1,4 addition. One, two, three, four. It's a 1,4 addition. It's a Michael addition. So the nucleophile adds like that. So it is a 1,4 addition. Okay. Michael addition. And where did we talk about Michael addition? Let me show you, refer you to the slide. And for the previous one, you can refer to slide 28. For this one over here. Slide 28. And for the Michael addition, we talk about Michael addition, conjugate addition, 31, 32, 33, yeah, 32, 33. Slides 31 to 33, you can refer to the Michael addition. And then the next one, what is the product of the following reaction? Now this is also a Michael addition. Okay, conjugate addition. Same slides you can refer to. So when you add the methoxide, what's going to happen? Now where do we have the alpha hydrogen, most acidic alpha hydrogens? You're going to find in here. This hydrogen, alpha hydrogen, is the most acidic hydrogen. So you will form an enolate there. CO, CH2, CO, OCH3. So you're going to form a carb anion right there. Okay, and then this is going to act as a Michael addition. That's lone pair, doesn't want to make it. Okay, good. So there is a lone pair right there. That is going to add in the 1,4 addition like this. It's a Michael addition. Again, refer to the page numbers. I refer in the previous one. So this will make it like this. O minus, a double bond right there. So the carbon will add here to this carbon. OCH3, and from the other side OCH3. And then the next step, so this ion will grab a hydrogen from a water molecule. See, if it is happening in basic medium, it would be the water molecule. In the basic medium, it would be water. Take hydrogen from the water and it complete formation of the product, which will be something like this. Reform the ketone. This one, this is going to be the product. Now which one is going to be? Carbonyl group, CHCOOCH. I see the product. You can find out which one is from this selection. That's number 20. And 21, what is the product of the following reaction? Again, this is through the enamine conjugate addition. It's another Michael reaction. Okay, so we can see what's happening here. Again, so the carbon over here going to attack this carbon and then open up. So this will give you nitrogen, CH2, carbon, carbon, CH3. 1, 2, 3, 4. 1, 2, 3, 4. 4 minus this. 1, 2, 3. And then the next step would be grabbing a H plus, and then also at the same time when you add hydronium and water, this would hydrolyze back to ketone. So it would be something like that. Okay. Yes, so that's going to be the structure. So which one is going to be the correct answer then? We have a carbonyl group. Yeah, I see the answer. So you can figure out which one the correct answer. And this also you find in page 31, slide 31. Okay, this information you can find in slide 31. Refer to that slide. What is the product of